Hello students, today we will learn about the concept of pH. pH is a measure of the relative amount of hydrogen and hydroxide ion in an aqueous solution. The water molecule will dissociate into hydrogen ion and hydroxide ions. In terms of molar concentration, water at 25 degrees Celsius contains equal number of hydrogen and hydroxide ions per liter. In aqueous solution, the concentration of hydrogen ions multiplied by the concentration of hydroxide ions is constant. That is, HKW equals to H plus and OH minus, where the brackets signify the molar concentration and Kw, that is nothing but the dissociation constant of water. The value of dissociation constant depends on the temperature. Dissociation constant at 25 degrees Celsius is 1 into 10 raised to the power minus 14, and at 35 degrees Celsius it becomes 1.47 into 10 raised to the power minus 14. Acids and bases, when dissolved in water, simply alter the relative amount of hydrogen ion and hydroxide ion in a solution. Acids increase the hydrogen ion concentration and decrease the hydroxide ion concentration, while the bases increase the hydroxide ion concentration and decrease the hydrogen ion concentration. pH is another way of expressing the hydrogen ion concentration. pH is defined as the negative logarithm of hydrogen ion concentration at the base pair. Therefore, if the hydrogen ion concentration is 1 into 10 raised to the power minus 4 moles per liter, the pH is 4. At neutral solution is one in which the hydrogen ion concentration exactly equals to the hydroxide ion concentration. At 25 degrees Celsius, a neutral solution has pH 7. At 35 degrees Celsius, a neutral solution has a pH 6.92. The common assertion that neutral solution have a pH is not true. The statement is true only if the temperature is 25 degrees Celsius. Now let's try to understand about the pH meter. pH meter is a potentiometer which measures the voltage between the two electrodes placed in the solution. The two electrodes used are a calomel electrode and a glass electrode. The calomel electrode is the external reference electrode whose electrical potential is always constant, where the glass electrode is the standard test electrode whose electrical potential depends on the pH of the test solution. The electromotive force of the complete cell is given by, that is E equals to E reference minus E glass, where E reference is the potential of reference electrode, which at a normal temperature is 0.250 volt, and E glass is the potential of the test electrode, that is a glass, which depends on the pH of the test solution. Then the pH of the solution can be determined by the following equation. pH equals to E glass minus E reference at 25 degrees Celsius. Substituting the value of E calomel, that is 0.0591. The electrodes. The calomel electrodes contain mercury chloride and saturated solution of potassium chloride. Each of these compounds exists in ionized state, although the extent of ionization may vary widely. The dissociation constants are as given in the diagram. The calomel electrode is dipped in a saturated solution of KCl, that is potassium chloride. The electric constant between the calomel electrode and the test solution is achieved by the KCl salt bridge through a fine capillary in the glass casing known as porous plug. The glass electrode contains a silver, that is silver chloride, and 0.1 molar HCl solution. The dissociation constant are as given in the slide. This electrode is dipped in 0.1 molar HCl solution. The calomel electrode is made up of thick glass that is impermeable to hydrogen ion. Therefore, its potential is independent of the pH. In contrast, in the glass electrode, the tip of the electrode is made of special thin borosilicate glass bulb, which is permeable to hydrogen ion only, but not to the other cation or anion. All these equilibrium reactions are delicately balanced, and when electrodes are connected, the electrons will move from positive electrode to the other. If now the electrode are placed in a solution containing high concentration of hydrogen ions, the calomel electrodes will not respond as it is not permeable to the hydrogen ion. The hydrogen ion pass through the glass membrane and neutralize the electron of the electrodal reaction, and hence electron flow from the calomel or to glass. When the test solution has high concentration of hydroxide ions, that is a high pH, the hydrogen ion moves out of the glass bulb, rendering a momentary negative charge, and hence the electron flow from the glass to calomel. Because of this passage of the ions, an electric potential develops across the glass electrode and calomel electrode, which results into the flow of current between the electrodes. The magnitude of this current depends on the concentration of hydrogen ion or hydroxide ions in a test solution. In the pH meter, the current is fed into the calibrated dial in a way that dial reading directly gives the pH of the solution. This is a diagram of the electrode where you can see the places where silver chlorides, reference electrodes, junctions, silver chloride covered silver wire, glass electrode, internal solutions is very well cited. Now, the next aspect is the operations of the pH meter. New or dry electrode should be soaked in water or in buffer of pH 6 to 7 overnight. The electrode can also be activated by soaking in 0.1 molar HCl for 12 to 24 hours. Electrodes should be stored in distilled water or as per manufacturer's instruction. Remove the beaker containing water, rinse the electrode with water and wipe gently with tissue paper. Dip the electrode gently into a standard buffer solution whose pH is accurately known. Make sure that the electrode does not touch the sides of or bottom of the beaker. Adjust the pH meter to the standard pH using the pH adjustment knob. Remove the standard buffer, rinse the electrode with distilled water and wipe it gently with tissue paper. Dip the electrode now into the solution whose pH should be found out. The dial directly read the pH of the test solution. After finding out the pH, wash and store the electrode in distilled water. pH calibration. The glass electrode does not give a reproducible electromotive force over a longer period of time. To get accurate result, the pH meter should be calibrated at least once a day or according to manufacturer's instruction. Calibration should be performed with at least 2 standard buffer solutions that span the range of pH values to be measured. For general purpose, buffers at pH 4 and pH 9.2 are acceptable. The pH meter has one control to set the meter reading equals to the value of the first standard buffer, and a second control which is used to adjust the meter reading to the value of the second buffer. For precise measurement, a 3 buffer solution calibration is preferred. Higher quality meters will have a provision to account for a temperature coefficient correction, and high-end pH probes have a temperature probe built in the electrode. The calibration process correlates the voltage produced by the probe with the pH scale. After each single measurement, the probe is rinsed with the distilled water to remove any traces of the solution being measured. Blotted with a scientific wipe to absorb any remaining water which could dilute the sample and thus alter the reading, and then quickly immersed in another solution. Next aspect is buffer solution. A buffer solution that resists a change in pH on addition of either acid or base. They are important for performing biochemical reaction at their optimal rate in vitro. In practice, a buffer solution consists of an aqueous mixture of weak acid and its conjugate base. The conjugate base component would neutralize any hydrogen ion generated during an experiment. while the unionized acid would neutralize any base generated. A Henderson-Hasselbalch equation is of central importance in the preparation of buffer solution. It can be expressed in variety of forms. For a buffer based on a weak acid, it is given as you can see on the screen. This is for weak acids, and this is for the conjugate acid of a weak base. Now, the next criteria is selection of buffer. When selecting a buffer for a particular experimental study, several factors should be taken into account. It should possess adequate buffering capacity in the required pH range. Buffers are effective over a range of 1 pH unit on either side of their pKa value. Select the one with a pKa as near as possible to the required experimental pH and within the range of that value. If the range is outside, there will be too little weak acid or weak base present to maintain an effective buffer capacity. The buffer should be chemically inert and not react or bind with biomolecules or other components, particularly for assaying activities of enzyme which require a metal ion for their functioning. Buffer components should be available in high purity and should not contain impurities which may interfere with estimation. Components should be enzymatically, hydrolytically stable and non-toxic. Maintain a pH that is minimally influenced by temperature, ionic composition, concentration or salt effect of the medium. It should not absorb light in the visible or ultraviolet range. This is all about the basics of the pH. These are my references. Thank you very much.